A casting can inherit a defect before the metal ever reaches the mold cavity. Slag fragments, oxide films, and other non-metallic inclusions can travel with the melt stream, and once they are carried into the casting, they may remain as discontinuities that affect surface integrity, machining, or local mechanical performance. The filtration step sits upstream of that problem. The structure here is not a flat screen with one opening per particle. It is a three-dimensional interconnected foam. Molten metal has to enter, divide, turn, reconnect, and pass through a large internal surface area. That geometry is the reason ceramic foam filtration behaves as a combination of flow conditioning and depth filtration rather than simple surface sieving. For steel filtration, the ceramic body must remain functional while the incoming melt is at casting temperature. Stabilized zirconia foam filters are commercially specified for service around 1700 degrees Celsius, placing them in the temperature range used for molten steel filtration. Actual suitability still depends on alloy chemistry, contact time, preheating practice, and the complete gating design. The filter body is based on stabilized zirconia rather than an unstabilized zirconia powder compact. Yttria or magnesia additions are used in zirconia systems to control phase stability, while the fired ceramic skeleton provides the refractory framework that has to survive rapid contact with a very hot melt. In a foam, that material choice matters at every thin strut and junction. High open porosity allows the filter to present a large internal capture surface without becoming a solid barrier to the metal stream. The zirconia foam range shown for this type of component is typically specified with roughly 75 to 85% open porosity. That value describes available void space. It does not by itself determine flow, because pore density, thickness, priming, and melt conditions all act together. Before steady filtration begins, the melt has to penetrate the porous network and displace the gas inside it. That requires sufficient metallostatic head or an equivalent pressure difference to prime the filter. A filter that is too restrictive for the available head can slow filling. One that is poorly seated can allow bypass around the edges. The filter therefore works as part of the gating system, not as an isolated insert. Once the network is primed, inclusions do not experience a single straight opening. They encounter repeated changes in direction and repeated opportunities to contact the ceramic skeleton. Larger particles may be intercepted mechanically, while smaller inclusions can deposit on internal surfaces through a combination of transport and interfacial interactions. The exact removal efficiency is therefore dependent on the melt, the inclusions, and the filter architecture. PPI means pores per inch. A lower PPI describes a coarser network with larger passages, while a higher PPI means more cells per inch and generally smaller flow channels. Finer structures can increase contact opportunities, but they also increase hydraulic resistance, so the highest PPI is not automatically the best choice. Geometry starts with the space available in the holder and the filtration area required by the melt flow. Common production formats extend from compact round filters around 35 mm in diameter to large 300 mm units, while square formats span from roughly 30 mm across to 300 mm. Thickness rises with size and required structural support. Non-standard design begins at the interface between the filter and the refractory seat. Diameter or length and width, thickness, edge profile, seating area, and PPI can all be adjusted, but the filter should still be selected around the molten metal grade, pouring temperature, casting mass, target flow rate, and available head. A correct fit is as important as the ceramic composition because edge bypass defeats the filtration path. In stainless steel and alloy steel casting, the filter sits directly in the path of a melt whose temperature leaves little margin for lower temperature filtration media. Stabilized zirconia is used here because the ceramic network can be engineered for this thermal window while maintaining an open flow path through the gating system. As the molten steel moves through the three-dimensional network, the path repeatedly brings suspended non-metallic inclusions toward ceramic surfaces. That is the practical value of the foam architecture. It creates many capture opportunities inside a compact filter volume rather than relying on one planar screen. The same porous network also redistributes the incoming stream as it passes through the filter, but the result depends on correct PPI, thickness, priming, and placement. In other words, the filter succeeds by managing a path, not by acting as a passive block. Precisely tuned to the gating system, a small piece of porous zirconia can influence what reaches the mold long before the casting begins to solidify.